Hello and welcome to the worksheet videos for worksheet number, what is it? 10, right? Worksheet 10, I believe, heaps and graphs. So we're beginning to move kind of towards the final part of this class where we're talking more about graphs and stuff. We're kind of wrapping up our general data structure techniques and going on to more broad data structures like graphs. So this first question we're doing here is about heaps. This is primarily a mechanical question, so I'm kind of just going to bust through it, but this is going to be a video where if you want to check over your process of doing it and make sure that you're doing every step correctly, or maybe you think you're going somewhere wrong in a step, you can do that because I'm just going to literally do every little motion, so hopefully you can just kind of memorize it and figure it out. Okay, so the first thing is draw the min heap, the results if we delete small element from the heap. So this is basically our kind of most basic, simple heap question we could ask you. If you use the min heap and take the min, how do you do that? Okay, so let's look at that. So I've redrawn this heap on the left, on the right, just so I can erase things really easily. So we're going to remove the min element, which is 0. So let's just take it off the top. Okay, so what do we do now? First thing we do is we go to the bottom rightmost element of the heap, and we're going to move that one up to the top. So we see that is this 9 down here. So I'm going to erase the 9, and I'm going to put it up here. Great, so now 9 is at the top. And now what we're going to do is we're going to do a process which you might hear it called bubbling down, you might hear it called sinking, you might hear it called reordering. There's a lot of names for it. But basically what we're going to do is we're just going to take this element we put at the top and we're going to swap it down with the minimum element over and over again until our heap is restored. This makes sense because, of course, 9 is not the min element, so it doesn't make sense to have 9 at the top of our heap. Okay, so we're going to look at 9's two children, 1 and 4, and we're going to say which one is smaller. 1 is smaller, so we're going to swap 9 and 1. Why are we swapping with 1 and not 4? Because both of them are smaller than 9, and the reason is, well, you could just do it yourself and actually see why. If we swapped 9 and 4, that would be great because now 9 is below 4, which makes sense. But the problem is now 1 is below 4, which does not make sense. So you would have to then swap 4 with 1, and that's the same thing as if you just kind of swapped the other way in the first place. So yeah, you always swap with the minimum element in a min heap. So 9 and 1. And if you were using a max heap, you would swap with the max element. You would just kind of flip these instructions around. Great. So now we say, okay, is 9 in place? Well, no, because it has children that are less than it. So we're going to swap again with the smaller child, which is 2 in this case, like that. And then we're done. This is all it is. All the heap properties are restored. Every element is smaller than its children. So great. That's the first part. Okay, now we're going to move on to B, which is draw a min heap if we insert these elements into an empty heap. So we're going to start from the beginning and build it up rather than just doing a min operation now. Okay, so this is the other side of heap balancing operations. We saw what it means to sink elements down, but now we're going to see what it's like when we swim them up or when we bubble them up, whatever it's called. So first thing we do is we add 6. 6 doesn't need to do anything because it's alone, so it's all good. Next thing is we add 5. So we are always going to add in the bottom rightmost position. So we're going to give 6 a left child because that's the bottom left to right that we're doing. And then we're going to swap 5 and 6 because 5 is less than 6. End up with this. Great. So we've added 6, we've added 5. Now let's add 4. So we add 4 in the continuing order of left to right, BFS order. Great. Then we swap 4 and 5 because 4 is less than 5. Great. Everything's all good. Add 3. So now we add 3 here. We're going to swap 6 and 3 like that. And then we are going to swap 3 and 4. Great. Now all of our properties are good. And 2. We add 2 right here. We're going to swap 4 and 2. It's 2 is less than 4. And then we see that 2 is less than 3, so we're going to swap 2 and 3. Right. All you have to do is compare it to the parent and swap if it's smaller. And again, if you're using a max heap, you compare to the parent and swap if it's bigger. You just kind of invert that operation. Notice that this is probably a simpler operation to do than the swimming down or the bubbling down because you don't have to worry about having 2 children because you only ever have 1 parent. It's a much easier question to ask. It's a little easier to write in code. But yeah, so that's all you have to do there. This is another one of those things where if you don't get it, I would just watch this video again, do some examples on your own, just do it until you can do it by hand, because then if this comes up on an exam, it will be, easy points. Okay, here, this is the kind of most involved of all three. So we're going to put things together. We're going to say, assume we have a binary min heap, which is what we've been working with before. I don't know why they're calling it binary now and they didn't call it binary before. It's been properly implemented, sure. We want to draw the heap and its corresponding array representation after each of the operations below. So this is a very big, important thing about heaps. And it's one of the things that makes them kind of cool as a data structure, is that the representation of heaps does not match the implementation of them. So in the past two questions, we've been drawing heaps as trees, right? And we've done a lot of work with BSTs, and you're probably familiar with BSTs, and you could say, oh, well, maybe if we wanted to implement a heap, we would implement it by having like a node class, and then we'd have like a root, and you'd have, left and right children, whatever. But you don't actually need to do that. And the way that heaps are implemented in practice in code is with a simple array. Might look something like this. I'll give it some indices. Because this mimics all the functionality that we have in our tree data structure. So all we're going to do is we are going to knock out element 0. We're going to make it a null. We're not going to use it all. We're going to start at element 1. This is the only time in this class that you're going to one index anything. MATLAB users rejoice. And basically, the left child of that node is going to be in index that is 2 times the current index, and the right child of a given node is going to be in 2 times the index plus 1. If that doesn't make sense, we're going to do it live and you'll be able to see a little bit better. Okay, so let's actually just start adding things. So first thing we want to do is into an empty heap, we want to add f. So we'll just put f over here. It's the first element, so it's alone. It's going to go in our first index. Great. Okay, now we want to add h. So just as before, we're going to add h as the left child of f, because f doesn't have a left child. And then we're going to add h here to our corresponding array. Keep in mind that f is held at index 1, so its left child is held at index 1 times 2, which is 2. Also, by the way, we are considering letters to be less than other letters if they alphabetically precede them. So h is greater than f, so we don't need to do any swapping here. It's a little weird that we're using letters now instead of numbers. I think it's weird, but whatever. Great, so nothing more to do at this point. Now we're going to add d. So d goes here, as you would expect, to be the right child of f, since it already has a left child, and also goes into index 3. Why is that? Because f is index 1, so if we multiply 1 by 2 and then add 1, we get 3. D, however, does need to be swapped up with f, because d is alphabetically before f. So we are going to swap like this, put d on top, put f down here, and the corresponding operation in the array is just as you would imagine. You just swap the two numbers, right? D goes up here, f goes down here. Great, now we're gonna add b. Okay, I'm gonna do all of the tree operations, then all of the array operations. So b is of course less than h and it's less than d. So what we're gonna do is we're gonna swap b with h. So we end up with this, and then b is less than d. So we're gonna swap b and d. So b goes up here, d goes down here. Same thing is gonna happen in the array. First thing we're gonna do is we're gonna add h into the next position, which is position 4. Then we're going to swap, or sorry, not h, we're going to add b into here, and then we're going to swap b and h, and then we're going to swap b and d. Same thing, just a different way of representing it. This is an easier way to understand visually. This is how your computer is actually going to do it and is more efficient. Okay, final thing we gotta add is c. So we add c as the child of d, as you would expect. C is less than d, so we're gonna swap c, d. Same thing over here, we're gonna add c, then c is less than d, c, d, like that. Okay, that's the first, all the insert operations here. Hopefully that makes sense. And so one thing to notice here is that if you read the array just left to right, notice it's the same thing as the BFS traversal order of this tree, right? If you go B, C, F, H, D, you just read it left to right, layer by layer. It's the same thing, B, C, F, H, D in the array. So that's a really easy way to just visually match things up and make sure things look good. Great. Okay, so now it's time to remove the min. So we're going to remove the min. We're going to remove B in both of them. Then what we're going to do is, as before, take the bottom rightmost element, which in this case is D, swap it up top. return of the king. D is it's back on top. So then we're going to swap down with the minimum element. So D is going to swap with C. Like that. Same thing is going to be mimicked over here. Great. D does not need to swap with H because D is less than H. So that's good. Then we're going to remove them in again. So now we're going to remove C. We're going to swap H to B on top. And now we're going to say, okay, do we need to swap? Well, D is less than H. So we want to swap with D. Notice that F is also less than H, but we're going to swap with D because we're going to swap with the minimum of the two. So we're basically going to end up with this. So we have empty element here, DHF. This, if you'll notice, is actually the exact same state that the heap was in when we just added these three things together. Go back and watch the video if you don't believe me. But that's how you would actually do this in an array, which is the way that you would actually implement it in code. Okay, so now let's move on to D. This is just a little conceptual question that is fun. So your friendly TA, Sadia, she challenges you to implement a max heap. So we were just doing everything with a min heap. Now we're going to do it with max heap. But basically the idea is you're like, oh, I already programmed a min heap and I don't want to reprogram everything to be a max heap. So how can you change the elements within the heap such that you can make it function as a max heap even though you start with a min heap? This is a great question to ponder on your own, but because it's just a conceptual question, I'll just give the answer right here. Basically, all you need to do is negate every element of the tree. And I will kind of show you a little example of why that works. So let's say you have a heap that looks like, you know, this or whatever. You have a heap that looks like this, sure. Every element, it's a really ugly 3 and 5. Let me draw it a little bigger. Sure, you have a heap like this. Okay, it's a min heap. So the minimum element is on top and then every child is greater than its parent. Okay, and you want to turn this into a max heap, you can just negate everything as you put it in. So basically the reason that that would work is because the heap fundamentally is kind of sorting things based off like magnitude right now, right? Like if things are bigger, they'll go below. And so if you negate everything as you put it in and you sort by magnitude, if you negate everything as you put it in, basically the magnitude will remain unchanged, but the actual like direction in which you're putting things in will swap. And that's fine if you already have negative numbers in here. So if you have like a -1 in here and then you switch it to a 1, it still works because now it's like the biggest, or now it's like, you know, the biggest element basically. But that's all you have to do. It's just a quick way to invert everything. Okay, I hope this is useful and I'll see you in the next question about graphs.